we looked at the simple case of essentially a linearly separable data set. All right. Now let's take a look at something that's a little bit more complex. So the next data set we're going to choose is this particular one. All right. Now this sort of is similar to what the XOR problem that we saw, right? You can see that you've got the cats over here in blue, which are zeros, and then you have the dogs over here, and you've got a large number of data points, right? So the question is, can this solve it? And the question was, I'd earlier asked, if you use some fancy activation function or other, is there any possibility that we can do it? Okay, so let's try it out and see if it will work. We'll use a learning rate of 0.03. We'll use a linear rectifier unit. We can use sigmoid as well, but it really works pretty well most of the time. It has some problems, but we'll discuss what those are later on. We don't need to look at regularization and other issues. Shall we start it off? We'll regenerate the data and let's start it off. Okay, so what are we seeing? The test loss is higher as expected than the training loss, but is it doing a non-linear separation? It's not able to do that, right? The best that it can do is basically draw a straight line. So basically what we're seeing is that even if we try to change the activation function to be, instead of ReLU, let's say we change it to sigmoid. Does this help? You can see that it's taking its time to converge, but it's not doing very well. You know, there's still a 40% loss, which means that it's essentially no good. And you can see that now the interesting thing is that you can see what the weights are for each one of these. So you can see that here the weight being used for W1 is 1.3. The weight over here is 1.3. And basically, if you look at this over here, you can also see the bias that it's using. It's using a negative 6.8, which means it's slightly shifted to the right. All right, you can see that it's somewhere over here. It's not around the 0, 0. You can also look at the pattern inside it. So when you look at, there's only one perceptron over here, but when you have more perceptrons, you'll understand what the difference is, one neuron. But you can clearly see that it's not solving the problem, all right? Let's try to add another neuron and see if that helps. So I'm going to add another neuron. And again, we're going to, let's say, regenerate the data and start it off again. And I'm going to go back to ReLU. Okay. Okay, here we go. Now, now a few things to note over here. The size, the width of this dotted line indicates the weight. Okay, the absolute value of the weight. So here it's negative 1.9, which is a little higher than, well, it's this is negative 0.35. This is negative, this plus 0.48, both of them are fairly small. And these two values are fairly large, so it's negative 2.8 and negative 2.8, okay? Now, what do you notice about this? If you look at this, the x1 is basically looking at the horizontal axis, right? x2 is the vertical axis. Now, both of these have somehow converged towards, and the lines are basically horizontal, all right? The lines are horizontal, which means that it's basically based on x2. And you can see that it's not really using x1. None of them are vertical lines. Both this line over here and this line, if you put your mouse on it, you can see the actual line that's separating. So this is slightly above. This is slightly at a slightly different angle, but both of them are essentially horizontal, and they're both using primarily x2, and that is obviously visible as well because the value of x2 is very strong. Okay, the weights are very strong. Neither one of them is using x1. Now, why is that? Because it simply started off randomly and it's just stuck. It's trying to find a solution to a nonlinear problem and stuck in some particular point. All right. Now let's restart it. So I'm going to restart it and see if we initialize it, will we get, because it'll start off with different initial random values and it'll come to a different solution. All right. So let's start it off again. Now you notice that it's come up with a completely different solution, but again, the losses are fairly high. It's about 25, 27% because, and again, it's using X2. Okay, for some reason, let's do it a few more times. Let's see if it always uses X2. Yeah, there's some problem with this system. It's always, no, in this particular case, now it's using X1. So I restarted it, refreshed it many times. Yeah, it's not doing a good job in terms of that. But basically the problem is that two perceptrons apparently are not sufficient to solve this particular problem. Okay. Okay. So what's the difference between this and the solution that we found? What's the difference? Three neurons, and this only has two. So let's add another layer. Okay. Let's add another hidden layer, and let's make it like this. Okay. So now let's see if it can solve the problem. Okay. So here we go. So it's doing a much better job. It's got, well, the training loss is down to 17%. The test loss is 19%. But it's doing a reasonable job. But you see, this is not exactly like the simple XOR problem. You see, it's more like a grid. Okay. It's a very sharp curve over here. And this is a very sharp curve. So it's hard to draw two straight lines, which earlier we could. All right. So even with this particular problem, if you have enough points, enough data, you won't find a good solution. The best solution that we found so far is 16% loss. Actually, training loss is not relevant. It's the test loss which is mostly relevant. So the test loss is almost 20%, which is not very good. Let's reinitialize it and see if we can come up with a different solution. And it takes time, of course. So sometimes you'll get stuck at a non-optimal solution, and it'll just get stuck over there. All right. And let's regenerate the data, restart it, and see what we get. Again, it is clear that for this particular problem, even this three neurons, three perceptrons is not sufficient to solve the problem. Okay. Now, what do we do? Should we add more layers, or should we add more neurons in the first layer? Let's do this. Let's reduce the number of hidden layers, go back to one, and see if within one hidden layer, if we can add more neurons. Do you think it can solve the problem? Any guesses? How many people think that adding with a single hidden layer, adding more neurons will solve this problem? Nobody thinks so. देखें, अब कर क्या रहा है? ये एक neuron जो है is drawing a line, right? So basically, if you think back, is basically drawing, each one of them is drawing a line. Now this one is drawing a separate line. But what we're saying is that a non-linear combination of these two lines, is it sufficient to solve this particular problem? And it seems like it's not, right? But if we add more neurons, if we add, not here, sorry, but if we add another neuron over here, they can, now it seems to start off with three lines, right? Each one of them can deal with a single line, with a single linear equation. And so it can actually have four straight lines. The question is, if you have three straight lines, can you solve this problem? So let's try it, okay? Let's see how far we get. So the loss is now still 24%, not very good. This particular one is classifying top and bottom. This is also doing something similar. All three of them are doing something pretty similar. I'll refresh it again, try to see if it does something different. It's not really coming. जी आपका सवाल था. So basically what it's doing is, as the data is going through this network, each one of these is doing something very interesting. And this is the beauty of deep learning, deep neural networks, that each one of these neurons is actually looking at one particular feature. And this particular neuron you can say is looking at one feature and it's drawing a line and it's saying that I'm looking at a very simple feature and it's a straight line and it's saying I can differentiate between those guys on this side of the line and those on this side of the line. All right. This other guy is also doing something similar. This is not a very good example. Let me look at another example. This is slightly better because you can see now the lines are slightly different. This particular neuron is saying that I'm going to look at one feature, which is this horizontal line is going to differentiate between the top and bottom, right? This neuron is very different. It selected a different feature. How did it come up with the feature? This was simply through an internal training mechanism, which we'll talk about later, which is basically the heart of one of the key algorithms, which is called backpropagation. Okay, that is what is used in training the algorithms, and we'll hopefully have time to discuss that before the session ends today, or maybe in the next lecture. So each one of them is picking a separate feature and is saying, well, I can do this. This chap is saying I can select this particular feature, which is saying the left side and the right side vertically. This neuron has selected a slightly different feature. It's saying I can separate those at with this angle. This one is taking a completely horizontal feature and it's saying I can separate it, okay, the top from the bottom. Now, between these three, they've done a reasonably good job while we're talking. In fact, training loss is 0, test loss is essentially 0 as well. So three neurons in the same layer, we're able to solve this problem. Okay, how is that? You notice that if you look at this particular neuron, it's got a very small weight for x1 and a very strong weight for x2. All right, and why is that? Because it's basically differentiating based on x2. All right, it's differentiating based on the vertical axis, and that's why even if you set the 0, by the way, you can do that. You can click on this and you can set the value to be 0. You can change these values. Okay, so now I've set it to be essentially 0. It changed it again, it changed to 0.16. But you can change these values. So it's basically neglecting x1 and saying I'm going to look at this particular feature of x2, which could be height, weight, or whatever feature that we actually presented to the of the data set. This one over here is got a very low weight for x2 and it's got a very high weight for x1. And what is it doing? It's simply selected x1 as a feature and it's differentiating between the values of x1. This, on the other hand, is got a weighted sum of those two, right? So it's got an equal weight. You can see the two lines are almost equally weighted. This value has a weight of -2 and this has a weight of -2.5, all right? So this is now differentiating between at this particular angle. So a non-linear combination of these three is now in fact able to solve this problem. Exactly how it's done it, it's a little hard to tell, right? Because it's going through a ReLU function, which is a combination. So if you looked at the actual equation and you plugged it in just like we did earlier on, you could probably figure out exactly how it's doing it. All right, but this is about the level that we need to know. We don't really need to know exactly what the equations are, but we need to know that yes, it can solve this problem. Now, still the test loss is 0.1%. Should we add another perceptron, another neuron over here and see if it does it even better? Okay, so let's add a fourth neuron over here and I'm going to restart it and I'm going to run it again. Okay. So it's got down to 0.0087. It's going through the training. It's going to take a little while. Hopefully, with 4, you can see now this is the same one that was earlier. It's differentiating based on x2. This one is differentiating based on x1. This one has selected an angle like this. And these two seem to be identical. So you can see that adding a fourth neuron is not really helping. These two are almost identical. So we're not getting anywhere. So it's almost the same. And we could just as well use 3 neurons, and you would get the best result. Adding more neurons is now simply taking more time, taking more resources, not really helping. Okay, G. So, say that again? Yes, absolutely. So, so every time I reinitialize it, when I stop it and I click on this, it reinitializes it. So each time I reinitialize it, the weights are presumably different. Like negative 0.48 over here, I redo it, and now it's negative 0.29. So it comes up with a completely different set of initial weights. Okay. And based on where you start, you could come up to the solution a lot faster or a lot slower. Right. So here's another attempt at solving the problem, and you can see that again it's doing reasonably well. And this seems to be, with three neurons, this particular problem is essentially solved. Okay. Now let's go to a more difficult problem. Now the next more difficult problem is we could select a spiral, or we could select a circular one. All right. So now I'll leave this up to you for you to test out, and you can now experiment and see. I look at the most difficult problem. This is a spiral. Let's take a look at this. See how we can solve this. So if we do this, let's say with one perceptron, one neuron, how well it does, you can see it's not doing a good job because it's circular and it's concentric, and that's not working. Interestingly, if I change the features, instead of having x1 and x2, if I make it x1 squared and x2 squared, if I change the type of features, in other words, instead of looking for length and height and weight of these animals, I picked a particular feature which was very interesting. Suppose that we picked the size of the tail, or we picked the the length of the ears, right? Now that could be very much more useful feature as compared to the height and weight, right? Because we know that cats, I'm not sure. So one of those animals have long tails and short, and so on. So if you pick the appropriate feature, maybe the results will be a lot faster. So let's change the feature. I'm going to use, instead of x1 and x2, I'm going to use x1, these two. So I think there's a way of removing this. I remember there was a way. Sorry? Okay, you're right. So now I've changed this, and I've changed the inputs to be x1 squared and x2 squared, okay? And I'm still going to use a single perceptron. Let's see if we can solve this problem. It is connected, but it's not working out. Well, let's add all of these. Okay, found a perfect solution. Error is 0.001. Now, why is that? If you look at it, the weights over here are very small, and the weights over here, even though you can't see them, but they're much larger as compared to these two. So in other words, if I now clicked on this and I remove these two, depending on how you initialize it, I suppose. Yeah, here you go. So we found a solution where these two are not connected, okay? And I'm simply using x1 squared and x2 squared, and I found a very simple solution, okay? Because I've changed the features. I'm using an appropriate features, and as you can imagine that, the circle, the radius of a circle is based on x1 squared and x2 squared. And that's why it's able to select not straight lines, but it's actually selecting circles now, okay? Now let's take a look at a different problem. So this is a problem which is even more complex. It's basically the cats and dogs are in a spiral, okay? And the question is now, let's go back to the original values x1 and x2, and see if we can solve the problem. Well, here obviously a single perceptron is not going to solve the problem. Let's see if we added 3 perceptrons, is it able to solve the problem? 3 neurons, it's not going anywhere. I'm going to add some more neurons. It's not going to get anywhere. I'm going to add another layer, okay? Now let's see what happens. So you can see it's trying really hard. It's coming up. Now look at the difference between the first layer and the second layer. Now notice the first layer is all linear, all right? This is linear, these are all linear shapes. But the second layer, which is a non-linear combination of the first layer, is now not linear anymore, all right? If you look at this and you look at this, you can see that it's trying to come up with non-linear shape. जो हम पहले कह रहे थे ना कि इस तरह की अगर आपको shape चाहिए हो, तो आप किस तरह कर सकते हैं? So this is exactly what it's doing, okay? Now sometimes what you'll see is that the test loss and the training loss are very different. In this particular case, you can see that the training loss is good, but you're seeing that the test loss is not very good. Now the problem that that sometimes happens is that there's something called overfitting. Okay, overfitting basically means that आपका जो training data है, उस पर आपने somehow आपने कोई solution उसके लिए निकाल दिया है. लेकिन as soon as you change the data a little bit, even though the pattern is still the same, but you change the data a little bit, the results are extremely bad, right? And that's when you see that the test loss and the training loss are very different, okay? You can see that this is the training data, and the training data par jo hai, it's getting overfitting. You can see that somehow it's selecting this particular range, but it's doing a pretty pathetic job, all right? I'm going to add some more layers and see if we can add, we can, you know, just try to overkill it, because this is a tough problem, and see how far we get. So I'm going to just add a whole bunch of neurons. Suppose I take 8 neurons over here and just put the entire force, you know, I've just thrown a whole bunch of resources at the problem and try to see कि क्या does it start, you know, getting better solutions. So you can try different versions, so you can actually duplicate this, okay? And because it might be stuck in a particular problem, so you can try to see, you know, this particular problem, you know, this is how it's getting there. This one is still working on it. But you can slowly see that it's trying to find solutions to the problem. And now the interesting thing to note that each one of those neurons in different layers is picking up different features, okay? The simplest first layer is picking very simple features. It's simply saying straight lines, all right? The second layer, on the other hand, is picking up higher feature. It's a combination of the first feature. And now this one has picked up a circle, all right? This one has picked up a slightly different circle. This one has picked up a slightly different region, okay? This one has picked up, now this, even the third hidden layer is picking up even higher level features. This one is picking up a feature which is a combination of maybe this circle and you know, some of these. So what's happening is that as you have deeper and deeper layers, you can have you know, features which are a combination of lower level features, okay? And that's the real beauty of a neural network. And while this is training, let me just show you this is from one of the papers. So this particular example shows you if you train it on a human face, for example, and the network is thrown on its side. So this is the input, these are the hidden layers, and this is the output, okay? So it's vertical. So basically what it's saying is that the first hidden layer is showing you very simple straight lines, just as we saw, right? The second hidden layer is now able to pick up parts of the face. So it's picking up, you know, part of, you know, the eyes, the lips, the ears, the nose and eyebrows and so on. And finally, the third deeper layer is picking up the entire face. So it's picking up different types of faces. So this one is picking up maybe a face with a long nose, another one is picking up one with a mustache, another one is picking up other features. So this is what the beauty of deep neural networks is, that as you add more and more features, you can actually build up the feature, the combination of features, all right? And this was never done before. This was never realized. And the real beauty is that you don't have to physically figure out what features to select, okay? And what combination of weights to select. In the past, what used to happen is that before deep neural networks came in, if you wanted to have a recognition system, a facial recognition system, you would manually have to figure out, well, what are the features that distinguish different people? And somebody would, come up with an algorithm which would say, okay, let's have one feature which is looking at the glasses, right? You would have a specially designed algorithm which would be selecting glasses, all right, people wearing glasses. Another algorithm may be selecting beards. Another one might be mustaches. Another one would be long hair, ears, nose, all kinds of features. And these would be manually, the algorithm would be defined by humans. Deep learning, on the other hand, says the data will generate the results. All right, we give it a bunch of data, we give it a large number of resources, and somehow magically, and that's where the backpropagation algorithm that we're going to talk about later on, that comes in, that somehow magically, if you give it enough time, it's able to find solutions. All right, and you come up with, this is all done automatically, right? You give it a large enough network, and you find that suddenly able to figure out features which we didn't even know existed. Okay, and a lot of times these features are not immediately obvious. You don't really know that, okay, there was this feature that we never even thought. So for example, you're differentiating between dogs and cats, and you give it 1 million images of dogs and cats, and all of a sudden you might realize, okay, here's a feature which differentiates dogs and cats, which we never realized. Okay, but somehow the AI engine was able to pick it up. So it's actually does it. It's smarter than the human brain to be able to pick out these features. G. The neurons individually are selecting certain features. Yes, you can say that. So. Okay, so right. So your question is, how do we? What exactly do we mean by feature? So I guess let me explain. Features could be the inputs at the initial point, but then the combination of these could also be considered as features. Okay, it depends on how you define it. But let's say, if you're looking at this particular result, right? So here you could say that this particular nose is a feature, okay? Or this mustache over here, or this particular eye is now a feature which is being selected by one of the layers in the network. So so if you look at this result over here, we can see that this neuron is actually selecting the feature which is a circular in nature, which is just this particular circle. It's selecting that feature. Okay, so it depends on how you define a feature, but if you don't restrict it to just the input features, then you could take a broader view and say that features could be defined at any layer. Okay. So yeah. So the initial features are very simple. You've got data in 2 dimensions, x1 and x2, and these are numbers between -6. If you look at it, these are just numbers between -6 and +6, and similarly x2 is between -6 and +6, right? Just numbers. They could represent anything. They could represent height, weight, whatever, but they're negative as well, so they couldn't represent real numbers, right? Sorry? Oh, I'm sorry. You got to remind me about that. Why is that? I'm going to stop the sharing. I'm going to share again. Okay, I think it's because I have maximized it. Okay, I got it. Okay, that is because it was in maximum view. So basically what I'm saying is that आपका I'm sorry सवाल क्या था? Right. So your question was, what are we feeding in? So basically here we're simply feeding in numbers, right? These are numbers, not just positive numbers, but negative, from -6 to +6. And similarly, for x1 and x2, there's just random numbers. But they've been grouped into such a way that they form the cats and dogs, blue and orange, orange and blue, right? So the orange could be one set of data, and you want to be able to differentiate it. So they're labeled differently. The orange ones are perhaps labeled as 0. The blue ones are labeled as 1. Okay, and you're trying to generate based on this neural network. You're trying to generate the output such that when you have an input which is one of these orange ones, it comes out as appropriate label, either 0 or 1. Okay, so I hope you understand how you're presenting the data. Would be much more complex. All right. So if you look at an image, if it's a simple, if it's 3-dimensional, you would actually, if it's in color, you would have RGB, red, green, and blue. All right. You'd have all of those colors. Then you'd have a 2-dimensional array. All right. So let's say if it's a 256 by 256 bitmap image in color. So you would have 256 by 256 by 3. That would be your dimension of the array. If it's simply black and white, it would be bitmaps. It would be a 256 or 1024 by 1024. Okay, so that's basically what you'd be giving it. Okay. Yes, yes. So you would actually give it. Yes, yes. So you would have 1024 by 1024. Your input would be actually 2024 points. If it's 1000 and 1000, you would actually present it 2000 inputs. Okay, so that, yes, 2000 features. Each one of them would represent 1 point on your bitmap. Okay, so so this becomes extremely large, as you can imagine, and that's why the amount of resources that you require are extremely high. So you can see that this is getting good. But here's a solution that I found earlier, I think. Yeah, here's one that I found earlier. I let it run for a while, and I was lucky and I found something nice. So this was using 3 layers, 8, 6, and 4. And you can see that it's essentially picked out the entire thing. And the loss, not just on the training, but the test loss is also extremely low. One of the things I also did was I introduced some noise, and that I think helped. But let's not talk about that. So you can see that if you look at what each one of those neurons is doing something very complex. Initially, it's very simple, the features. As you go deeper into the neural network, it becomes more complex. This is picking up different types of features. And this you can see is a even more complex set of features. And ultimately, when it's combined all of that, it's able to actually find a spiral. Okay, so so this is a great playing ground. You can try different sets. You can, I think there's a way to even actually look at the code. But let's stop over here as far as the neural playground is concerned. And now the next question is, how does it actually work? Okay, so far it was just a black box. And now the question is, let's try to see. Let's go deeper into it and see how it actually works. Okay. So this is again another look at the same data. You can see that low-level features, mid-level features, high-level features. So as I said, there are 2 things which now we're going to study, and now it becomes a little bit more mathematical. But this and probably the next lecture will be about the extent of the math. So we're not going to do a lot of math. It's going to be relatively simple math, but you need to have a few things under your belt to be able to follow this. All right. So I'll go relatively slow. I'm sure some of you have forgotten some of the calculus and so on. But basically, the basic algorithm is called backpropagation. Okay. Backpropagation is a way that you have a deep neural network. So let's say we have one of these networks. Let's say we have one of these networks that we saw earlier. Now we need to train the weights on each one of them, okay? So we need to figure out what the weights are over here. This could be W12 and so on, and WN, and so on. This could be another set of weights, this would be another set of weights. So the question is, how do we actually, starting with a completely random set of weights and giving it a large number of data, okay? So we keep giving it a large number of data, right? So deep neural networks relies, one of the things I has a problem with is that it is not going to work if you have a small set of data, okay? If you just have a dozen cats and dogs and you expect it to work, it won't work. But if you have a million sets of pictures of cats and dogs, it'll work very well. So you need to give it a large amount of data, and then you need to make it train for a long time. Now the basic algorithm is that it uses something called backpropagation. And backpropagation basically says that I'm going to figure out the weights over here, and then I'm going to use that to train and figure out the weights in the layer before. And I'm going to use that to figure out the weights over here. And then I'm going to repeat the whole thing again, okay? So once I've figured out the weights in this particular direction, I'm going to repeat the whole thing, and I'm going to keep on going. Okay, so it's going to be a cycle, and that's what you're seeing. The iteration that's happening is basically a continuous cycle, depending on, if you leave it for a day, you could leave it for a month, all right, or a year. It'll just keep on training. What does it use? Well, it uses labeled data. Okay, so it is using labeled data. In other words, when you're training it, it needs to know what is the correct answer. It needs to have the correct answer. And based on that correct answer, it's going to say, well, what is the answer that you're getting? So this is what you're getting. And the labeled data, we're going to call it as y hat. Okay, so y hat represents the set of data which is the correct set of answers. So for example, you have a whole bunch of, you're trying to, let's say, classify between 3 sets of answers, right? So suppose you have a goat, cat, and a dog, right? So you need to have 3 outputs. And this is going to be a 1 if it's a goat, this is going to be a 1 if it's a cat, this is going to be a 1 if it's a dog, right? And for each one of these, you've got the correct answer. So it's going to look at the answer that you're getting, and it's going to compare it with the answer, the label, and it's going to calculate a loss. Based on that loss, it's going to go backwards and train and figure out the weights. And it's going to slightly modify the weight. So it's not going to suddenly, in one iteration, find the correct result. All right, it's going to say which is the direction I need to go. All right, and then it's going to say, well, I've slightly tweaked this layer. Now I'm going to tweak the next layer, and I'm going to slightly improve that. But I'm going to hopefully go in the right direction. That's important. If you want to get to your destination, you have to go in the right direction. If you're going in the opposite direction, you could keep walking forever, but you'll never get to the right destination. So the idea is that to be able to choose an algorithm which points you in the right direction. So this is what the backpropagation algorithm is doing, and it's going to keep on training. This is going to be one iteration, then it's going to loop back, and it's going to look at the next set of results. The next set of results may be another batch of data, okay? And that could be the same batch of data, it could be another batch of data. So if, for example, if you've got a large amount of data, suppose you're training on Pakistan's population, all right, 200 million people. You've got data of all of that. Now you can't train it at one instant in all of that. So you might say, well, I'm going to train it on 1,000 people, then I'm going to train it on the next 1,000 people, next batch, and so on. And I'm going to keep on improving, okay? So that's how it typically works. It uses data based on batches. And ultimately, once you've done the entire 200 million, you might actually go back and start again, all over again with the first batch, okay? So that's basically the backpropagation algorithm. The backpropagation algorithm is based on something called a gradient descent algorithm. Now, the gradient descent algorithm basically says that you have to point me in the right direction. Okay, so when I said that the weights have to be slightly modified, the question is which direction do I change the weight? Okay, do I go in this direction or I go in that direction? And the linear and the gradient descent algorithm tells the algorithm which direction do you need to go. Okay, keep up as well. I'm not sure if I understand your question. फिर से कहिए. ठीक है. ठीक है. ठीक है. Yeah. This is the backpropagation algorithm. This is the big backpropagation algorithm. This is how you're going to train the weights. Now the question is individual weight को अब आप किस तरह modify करेंगे? ठीक है? That uses the gradient descent algorithm. Now gradient descent is going to say I'm looking at one weight. How do I change that weight? आप उसको किस तरह modify करें? ठीक है? So the backpropagation is the macro picture, and the gradient descent is now the micro picture. And it's a combination of both of these that will solve the problem. Okay. So now let's take a look at the gradient descent algorithm. Now the gradient descent algorithm is gradient descent. It's basically based on the idea that, let's say that you have a particular weight. Okay. Now we try to modify a particular weight. All right. This is not looking at the entire weight. We just trying to say कि ये जो पिछला weight है, इसको हमने किस तरह modify करना है. Okay. Now, if we try to figure out what an error is, so let's say that we've defined a loss. Okay. Now, how did we earlier define the loss? We said that we've got y hat, which is what we're trying to get. Okay. And y, which is what we have got. All right, so let's say this is y and y hat. So suppose that we were training cats and dogs, and the first three were supposed to be cats and the next three were supposed to be dogs, right? So what is the correct answer? Correct answer was supposed to be 3 zeros and 3 ones, right? Remember that we identified dogs as ones and cats as zeros. So if we have 6 pieces of data, then what we expect is that the answer, every time we feed it one particular set of values for x1 and x2, we should get a 0. All right. So if this was suppose a 2 and a 2, we should get a 0 here. But now initially the weights are random. We're not going to expect the correct answer. It might come out to be that this is a 0, possible, but it's quite possible that when we feed in, let's say, a 5 and a 2, we're expecting again a 0. Right? We're expecting a 0 over here, but what do we get? Let's suppose that we get a 1. All right. If we're getting a 1, what's the error? All right. So the error is basically y hat minus y, which is the loss function. All right. In a basic, simply we said the error over here is 0. In this particular case, let's say we are over here. The error is, what is the error? -1. Suppose this is a 0, this is 0, this is a 0. Here the error is 1, positive 1. This is a 1, this is a 0, and this is a 0. This is again a +1. All right. So you can calculate the error, and then you can say, well, is this what we want? Now, typically, some of you might have studied, for example, a linear regression. When we are trying to do a linear regression and we're trying to fit a line through a set of points, we could use a simple error, all right? But a simple error a lot of times is not very good, okay? Simply because it has a problem. First of all, the polarity is there, and secondly, it's been shown by mathematicians that it's not the best way. A better algorithm is mean square error, right? So what you could do is have a mean squared error algorithm, which simply says that I'm going to take a sum of all the y hats, okay, minus y, So these are y sub i's. I'm going to square these two, and I'm going to take the mean of them, right? So this is the mean square error. It simply says that every time I have an error, I'm going to take the difference between the two, but I'm going to square it, all right? And then I'm going to, there's also something called root mean square, which means you take the root of that, or you could simply take the square of that. Okay, there are different algorithms. But let's assume that we're going to be taking the mean square error. In other words, we simply take all of the errors, we square them individually and take the sum and take the mean of that, okay? So this is the algorithm that I'm going to be using for at least in the near future. You could change the algorithm completely, that's completely up to you, all right? Now, let's say we define the loss, and I'm going to erase some of this. And let's say that we tweak we have an initial value of a W, and for that we get a particular value of a loss, all right? Suppose this particular loss comes out to be 100, and we pick a particular value of W, let's say we pick a value of 10, all right? Now the question is, what should we, should we increase W, should we decrease it, by how much should we change it, and so on. Now, if you have an equation, if you can figure out an equation that tells you the relationship between the loss as a function of W, then you can plot it, okay? And suppose that we get an equation which looks something like this, all right? What does this tell you? This tells you that at this particular point, for a value of W equals to 10, the loss is quite high, but there is a point, just by looking at it without actually doing a mathematical analysis, but just by physically looking at this equation, we can tell that that there is a point over here where the loss seems to be minimum, right? Maybe this is a 0.25, okay? Now the question is, how do we get there? So if we have an equation for it, do you think we can solve this problem? Do you think there is a solution to this problem? Suppose we had a very simple closed form equation. So we actually knew what it looked like, right? So suppose it looked like something like ax squared plus bx plus c, all right? It's a typical quadratic equation. If you wanted to find the minimum maximum of that, how do we do that? Remember your calculus? Derivative, and you set the derivative to 0, right? So you take the derivative of that and you set the derivative to 0. So when you take the derivative, all right, you take, if this is your equation, f of x, and you take df by dx, and let's say you get 2ax plus b, and you set this equal to 0, what does the derivative represent at a particular point? It represents the slope, right? So the derivative, the 2ax plus 2b, or whatever value it is, that represents the slope at this particular point, right? Now we know that if it is equal to 0, the slope over here is essentially 0, right? So the slope here is 0. The slope here is most likely, is it a positive slope or a negative slope? It's a negative slope. It looks something like a -2, right? It's sort of sharp. It's -2. So if you know the slope, now if you know the actual equation, it's a closed form equation, right? Then the solution is very simple. How do you find the solution? You simply take the derivative, you set it to 0, and you solve for it. So you can easily solve for this particular equation. 2ax plus b is equal to 0, and your answer is, x is equal to minus b upon 2, right? So that tells you exactly at one go, you can find out exactly where the optimal point is, all right? And that's it. You found the optimal solution where the loss is minimized by taking a particular value of W. However, guess what? Do you think that this equation is known, and is it that simple? No, it's, if you remember, as I said, I showed you there could be features which are extremely nonlinear. This could be an extremely complex equation. This equation doesn't have to be that simple. It could be something like, it could be something which looks like this. It could be something even more complicated. It could be, it could be something like that. So suppose that you start over here and we're trying to find the optimal solution. Does anybody recall any method that they might have studied in one of your calculus courses to use an iterative method to get to the optimal solution? So let's assume that I'm not going to take this particular example. Let's say that I take a very simple equation, simple system. Now the equation f of x is not a closed form solution. You can't differentiate that as such. But what you could do is you could find the slope at this particular point. So if you could find the slope, let's say over here, you could find out what df by dw, well, this is actually a weight. So I'm going to call this a w. So this is just one of the features. This is the loss, all right? I'm going to call this as e hat, which represents the mean square error now. This is not the simple error. E I'm going to represent as the simple error, which is y hat minus y. But e hat is the mean square error version of it, okay? Now suppose that we could calculate df by dw at this particular point, okay, when w is initially equal to, let's say, 10. And we could find the slope over here. And we find out that the slope over here is -2, okay? And does that give us a clue as to which direction we should move? Which direction should we move? To the right. Why is that? Why shouldn't we go in the opposite direction? Because you can tell from intuition that if the slope is negative, then you've got to move forward. And suppose that you were over here, that let's say this is 25 is the optimal solution. Suppose that you were at 50 and the slope over here would be negative or positive. So the slope would probably be a +2 or +3, let's say over here, okay? So if the slope is positive, then you need to go in the reverse direction. If the slope is negative, you need to go in the positive direction in one dimension, all right? This is simply looking at a 1D problem. So it's very clear that suppose that you have an iterative solution that you want to find out for n+1 and you have wn, okay? So wn suppose is 10, then you're going to use the slope over here, df, or rather not df, but actually, what should we use over here? What do we need to differentiate? de, right? So we need to find out the slope of the equation where e, the error, is plotted against the weight, okay? So we're going to find the slope of de with respect to the variable, the feature that we're trying to tinker with, we're trying to modify, all right? Now, what should there be a negative sign over here or a positive sign? Negative. Why is that? Because we know that when this is negative, so let's say it was -2, we need to increase wn, right? If this was 10, we need to actually go in the positive direction. If this slope was positive, if it was +3, we need to go in the negative direction. So in other words, we need to go in the opposite direction of the slope. So this will have to be a negative slope, okay? So this has to be negative, very important. And this is all about the gradient descent algorithm. So what we're talking about here is the gradient descent algorithm. So you can see that the gradient descent algorithm basically relies on an iterative method. And the important thing over here is which direction, right? And this, we've already figured out that you simply take the slope of that particular point and you change the sign, and that's the right direction. Now the question is, should we take a big jump or should we take a small jump? All right. Now, if suppose I added a value r over here, and remember we had a learning rate. That this here is the learning rate. Okay, so r is the learning rate. learning rate. And now, what do you think happens if we make R very small? And what do you think happens when we make R very big? Okay, so we saw that if we took R very big, we took 10, it didn't converge. Okay, so what's basically happening is that if you take R very small, then you're going to take very small steps. Okay, if you take R to be very big, so let's say that we take R to be extremely big. Okay, so let's say that we have this particular solution, right? We start over here and we say, well, we're going to go in the positive direction, and this is 10, and the learning rate is very large. So we actually overshoot. Okay, we go right on the opposite side, and now this guy says, well, wait a second. Now the next value, this is, let's say, W0, and we come up with W1 over here. Now W1 says W2 is going to be calculated based on the negative of the slope. The slope over here is now -3, suppose. Okay, and so it's going to take a big, large number, and it's going to go an even bigger step in the opposite direction. So what could happen, it might end up over here, right? And this guy says, now I'm going to take another big jump in the positive direction, right? Because now the slope is negative. So this guy might end up over here, right? And then the slope is even steeper over here, and you might say, I'm going to take a bigger jump over here. So you come over here and you keep on going, and you can see that you're not actually converging, instead you're diverging. So if R is too big, you are diverging, right? But what if R is too small? So if R is too small, you start over here and you take a really small step over here, all right? And then what happens over here? Does the slope become smaller or bigger? Slope is now going towards the slope of 0. It was over here, let's say the slope was -2. Now the slope is going to become -1 perhaps, right? So now you're going to take an even smaller step, because it's the steps you take are proportional to the slope. Okay, the learning factor, the learning rate is the same. You're going to take a smaller step. Now what happens over here? Does the slope become smaller, even smaller? So over here, if the slope was -1, the slope over here may be -0.5. All right, so you're going to take an even smaller step. All right, and then subsequently you're going to take an even smaller step. So basically you're going to take smaller and smaller steps, and the steps might become so small that it's going to take you an infinite amount of time to actually get to the final result. Okay, so now the question is, how do we choose the optimal rate? I mean, we don't really know. We could take 10 on one side and we never converge, or we could take quadruple 0, 1, and it's taking forever. So you could experiment, and there are lots of algorithms that we'll study later on. There's a whole, this is basically, deep learning is an optimization field. It's actually a very mathematical field. If you go deep down and try to figure out, if you want to do research in this area, it becomes very mathematical. All right, this is basically an optimization problem. But most of the users, like this particular course is not really a course where you're trying to come up with new algorithms. The course is basically an applied nature, right? So you need to see what are the well-established algorithms, and you take the well-established algorithms, and there could be a dozen different algorithms, and depending on the kind of problem that you have, you may want to use a different algorithm. Okay, so the question is, which algorithm to use? Now there are some very well-established algorithms which actually use not a fixed learning rate, but they modify it, right? So you start with big steps, but if you see that you're diverging, then you change the steps to be smaller, all right? If you're taking too many small steps and not getting anywhere, you change the steps to be bigger, all right? So eventually you try to get to the optimal solution in the fastest possible, and then we look at different algorithms as well. So here's a particular example that I've chosen over here, just to highlight the actual case. So let's say that we this particular line, the black line, solid line, is what we're trying to solve for, all right? And we start with with initial W0, which is equal to 10, all right? We assume that the initial slope is, let's say, -2, okay? So the slope over here is -2. What was the equation? So this was the key equation. Wn plus 1, that means the n plus 1th iteration, all right, is going to take the previous value of the weight, and it's going to take the learning rate multiplied by the slope of the equation, and it's going to take the slope over here. Now, one of the things I haven't told you is how do we actually calculate the slope, okay? This is probably going to be something that we'll likely talk about next time, or we'll try to start it off today. But we have a learning rate, which tells us how big a step to take, and we have a slope. So we've got a slope over here. What would be the new value over here? Let's assume that we take r is equal to 1, okay? So what would be W1? It would be 10 minus -2 times 2, right? So this comes out to be 10 plus 2, which is 12, all right? So W1 becomes 12. And now let's assume that the slope over here at this particular point, this is 12. We jump over here. This is now W1. We come over here, we take the slope over here. The slope over here comes out to be a bit less. You can see it's probably -1, right? So the slope over here becomes -1. Now we take 12 minus 1. Sorry, am I making a mistake over here? I did that wrong. So minus r, which is 1, times the slope, which is -2, right? So the answer is right. Just the steps were wrong. So again, 1 minus 1. So this becomes 13. And then at 13 again, so this is now W2, which is equal to 13. So you can see that the steps are becoming smaller. We started with 10. The first step was +2. The next step was +1, all right? Now at point 13, we find out the slope, and let's say that the slope is -0.5. So this becomes 13 minus r times -0.5. What does this become? 13.5. So now the step is becoming smaller and smaller, okay? So we're taking smaller and smaller steps, and eventually, if you do this long enough iterations, hopefully will you get to the actual, using this iteration, will you actually get to the solution? Let's say it's 25. Do you think you'll actually get to the number 25? Probably never, right? This will converge and get closer and closer. It will get infinitesimally closer to the solution. In infinite time, it will reach the optimal solution. But in finite time, it will actually probably not reach the optimal solution, okay? But you can get as close as necessary given enough time and resources. So this is a quick look at the gradient descent algorithm, and this is a fundamental equation that is going to build up later on as we look at the backpropagation algorithm. Okay, so I'll label this as equation number 1. Okay, so this is where we are. So now let me just show you the kind of problems that exist in real world. Okay, so this is a depiction of the kind of problem. Now this was what I showed you was one-dimensional, right? There's only W1. Here they're labeling it as theta1, but you can think of this as W1, and W0 or W2. Right now, this is in 2 dimensions. So here you've got a loss function which they've got labeled as J, which is a typical way of demonstrating the loss equation, which is E hat, which I use as E hat. And now what they're saying is that you're trying to find the optimal solution, and the optimal solution could be extremely complex. In this particular equation, in this particular 2-dimensional graph, what you see is that you start off over here, all right? And where do you go? Now you need to modify not just W1, but the other weights as well. So you need to define exactly how you go in 2 dimensions. So you're going to choose the incremental value of W1. You're also going to choose the incremental value of W2, and you're going to take a particular step in a particular direction. So they're showing this as, you know, a step in this particular direction. Now, why is this called gradient descent? Okay, and this is also often called the steepest descent. So ideally, you want to, it's like being on a hill, you're in the middle of a hill, and you're trying to find the valley where you find the optimal solution. Okay, now sometimes you could actually have multiple solutions, and you could also get stuck in a non-globally optimal solution. So this is a local optima, but this is not a global optima. So this is a global optima, right? So if you're going down over here, and if you start at the right spot, you could hopefully get to the global optima. But suppose that you started off over here. Do you think you'd get to the global optima? No. You'd probably go down this particular hill, all right, this particular valley, and you'd get to a local optimum, all right? Once you're stuck at a local optimum, will the gradient descent algorithm help you? No, it'll just keep on saying, okay, you're going to get closer and closer to the local optimum because simply looking at the local gradients, right? So actual problems are much more complex. So this is perhaps a more real life depiction of, you know, a 2-dimensional, and this is just 2 dimensions, weights of two dimensions, and you're trying to find a solution to this real world problem, right? Now you can see that there could be thousands of local optima, and there could be maybe one global optima over here. But imagine that you're starting off anywhere over here, right? You could be starting off at any one of these points. Imagine how difficult it is to find a global optima, all right? So how do you do it? Well, this is where, you know, that's why you have hundreds and hundreds of papers being published, because they try to find good solutions to these problems. You might find one paper which finds a good solution. If you had to find a solution to this problem, how would you find one? Let's say that you're using gradient descent. Remember that when I was using the playground, sometimes I got stuck, right? What did I do? I reinitialized it to another value. And what would happen in reinitialization? I would go to a completely independent point. So what you could do is you could try one particular solution. Let's you find a local solution over here. But do you know if it's a global solution? We don't know. What you could do is reinitialize it, jump to a different point over here or over here, and see where you get, okay? And then see, is that solution better or not? So you could try a whole bunch of different solutions and see, does any one of them get to be a better solution? So you could come up with your own algorithm. All right, this is just an algorithm that I came completely, you know, sitting right over here. So one could come up with different algorithms, and of course there are some algorithms which are better, other algorithms which are worse, which try to find an optimal solution. Okay, so we're going to stop over here.